Okay, so the last factor that affects the discharge of ion during electrolysis is nature of electrode used. You see, some electrode do not influence the ions that will be discharged during electrolysis. Actually, these electrodes are called inert electrode. Any electrode that doesn't influence the ion that will be discharged during electrolysis are called inert electrode. Now, platinum and graphite are assumed to be inert electrode, although platinum can be attacked by liberated chlorine, and same with graphite. Graphite is made up of carbon, can be attacked by liberated oxygen. And so, but you see, most electrodes actually influence the discharge of ion during electrolysis, and we can see some of this effect of nature of electrode in the electrolysis of brine. During the electrolysis of brine, brine simply means concentrated sodium chloride. You see, mercury is used as the cathode, and at the anode, graphite rods are used. And for the electrolysis of brine, sodium is discharged instead of hydrogen. We still get to that actually. We'll talk about electrolysis of brine later during the use of electrolysis. But take note now, at the cathode, what is competing there is sodium and hydrogen. But sodium is discharged. That's because sodium is quickly joined to mercury because mercury has affinity for sodium, and that influences the discharge of sodium at the cathode, which shouldn't be, because not on a norm, not even the concentration of sodium would make sodium to be discharged. And by effect of position, hydrogen should be discharged. But sodium is discharged during the electrolysis of brine. Another case where we see the influence of nature of electrode is the electrolysis of copper 2 tetrahydroxide using copper as anode and using copper or any other metal as cathode. So let's take that now. Electrolysis of aqueous copper 2 tetrahydroxide using copper as anode and platinum as cathode. Please, the emphasis here is using copper as anode. That's where the influence takes place. Whatever is as a cathode doesn't really matter. And that's because ions from the electrolytes is what is discharged at the cathode. So let's illustrate this now. Now, take note that at the cathode, something happens. Copper and hydrogen migrate to the cathode. But obviously, by effect of position, copper is discharged because copper is the lower ion in the activity series. So copper is discharged. Let's have a diagram for this. This is our simple diagram for electrolytic cell. Doesn't mean electrolysis, but doesn't mean this is how the electrolytic cell used for this is. It's this just for illustrative purpose actually. I'm assuming that this is the anode made up of copper. So you see copper anode. And here we are using platinum. You could have used copper as well. It doesn't really matter. But here is copper 2 tetrahydroxide aqueous. Means it contains water. Doesn't really matter if it's concentrated or dilute. So that's that about that. Now, mind you, this is CuSO4 aqueous. And so what quickly happens here is that two ions migrate here. We have Cu2 plus and hydrogen. And so copper quickly accepts 2 electrons here and be deposited here. So you can see that, you will notice that the body of this platinum gathers copper on it. And that's because copper is simply being discharged. And so we can say at the cathode, copper and hydrogen migrate to the cathode, where copper is discharged because of its position in the activity series. And so that's that. So we have it like this: Cu2 plus accepting 2 electrons to be discharged as copper. And that is reduction. Now, at the anode, you see 2 ions migrate here as well, which is the SO42 minus and OH minus. Now, you would expect OH to be discharged based on the fact that it is the lower ion in the activity series, but that does not happen. So if OH is not discharged, then we are left with SO42 minus. But not even SO42 minus will be discharged. So neither SO42 minus and OH is discharged. So what then happens? This copper solid here, which is the electrode, ionizes and goes into solution. The question is, why does this happen? It happens because that is the easiest thing that can happen. You see, when we get to the atomic level, event occurs based on what requires the least energy. So the process that requires the least energy is copper anode ionizing and giving out its electron. Now, why is this actually happening again? And is simply because in this electrolyte is made up of Cu2 plus, SO42 minus, H plus, and OH minus. And so there's a copper 2 plus in the electrolyte. And the copper solid is saying that and saying, I am Cu solid. And I'm saying Cu2 plus. Why don't I ionize and become Cu2 plus? And that's eventually what happens. So, copper solid, I'll put it that neither SO42 minus nor OH is discharged, but rather the copper solid ionizes and goes into solution, leaving its electrons behind. Okay? So, let me clean this part now. And so what happens here is that copper, which is the anode, ionized, turned to ion, Cu2 plus, and this ion moves straight down into the electrolyte to go and meet the other copper it is seeing, and then give out its electrons. And this process is known as oxidation because electron is lost. Now, mind you, the overall reaction appears as though for every copper that comes from the electrolyte and gets to the cathode and becomes discharged, and that copper from the anode goes into ion and becomes Cu2 plus. So at the end of the day, the copper from here is simply being discharged to this place, and eventually the whole anode becomes depleted, being consumed. It is consumed, and no more copper is left here. The rod becomes tinier and more tiny and more tiny and more tiny, and then this grows fat because copper is being deposited. So overall reaction is as though copper is being migrated from being transferred from the anode to the cathode, and that's what happens. You see, this principle is being used during electroplating of one metal by another, or during purification of metal. Okay, electroplating of one metal by another, or purification of metals. So take note, this often happens when the electrolyte used contain the ion of the anode. You see, for instance, now, if I want a transfer of silver from the anode to the cathode, it means that I must use a silver electrolyte. And so, if I have a substance here and I want the body to be covered with silver, what do I need to do? For instance, go and use maybe silver chloride or silver 5. But mind you, you must use a silver anode. At the end of the day, the silver 5, silver will be discharged at the cathode. But at the anode, the NO3 or the OH will not be discharged. Rather, the silver, seeing the silver ion in the electrolyte, goes into solution. So this is the basic principle here. Uses of electrolysis. Electrolysis is used for the following. 1. Extraction of metals, e.g. the sodium, aluminum, magnesium, calcium, zinc, and non-metals as well, not just metals, such as hydrogen, fluorine, and chlorine gas. Now, under use of electrolysis in the purification of metals, e.g. copper, mercury, silver, gold, these are the metals that are below hydrogen in the activity series actually, and there's a reason for that. Next is electroplating of one metal by another, and lastly, preparation of certain compounds such as sodium hydroxide, chlorine, and hydrogen gas. So let's take the very first one now, extraction of metals and non-metals. All of the metals listed here, they are mostly prepared or extracted using electrolysis of their molten compound or fused compound. You know, why are we saying molten compound now? For instance, in the extraction of sodium, sodium chloride is used, but a molten sodium chloride. And what does a molten sodium chloride mean? Remember, sodium chloride is dissolved by action of heat. And so simple now, the sodium chloride just ionizes into sodium and chloride ion. There is no water here because it's not dissolved by water. So once you are using a molten compound, I mean not concentrated sodium chloride or dilute, all of those are aqueous. You are not using aqueous, you are using molten compound. Obviously, only sodium migrates to the cathode now, and only chlorine migrates to the anode. Obviously, it's not competing with anyone. It will be discharged, and chlorine is not competing with anyone. Itself will be discharged. So whenever you want to extract all of these metals, you know, we use electrolysis of their molten compound. We can't use electrolysis of their aqueous substance, and that's because whenever it's aqueous, they would eventually compete with hydrogen. It doesn't matter if it's dilute, it doesn't matter if it's concentrated, they will compete with hydrogen. And obviously, hydrogen being lower than any of these, hydrogen will be discharged or be sacrificed in that electrolysis. So that's why we use electrolysis of the molten compound to obtain all of these metals. Now, let's look at the second one, purification of metals. Purification of metal. A good example is the purification of copper. You see, let's say you have an impure copper and you want to purify that copper. All you need to do is go to the market and buy a pure copper and a copper electrolyte. Let's say copper 2 tetrahedrals of a 6, that is CuSO4, or copper 2085, or copper chloride, any copper electrolyte. Now, what happened is that the copper you are buying from the market, the small pure copper you buy from the market, the copper rod you buy, is used or serves as the cathode. While the impure copper ore you want to purify is used as the anode. Now, this is the electrolyte. Let's say we are using copper 2 tetrahedrals of a 6. What then happens? Well, the copper 2 to the 6 ionizes into copper 2 ion and SO4 2 minus, and what ionizes into hydrogen ion and hydroxide ion. All positive ions move to the cathode and all negative ions move to the anode. Now, you see, both copper 2 ion and hydrogen ion migrate to the cathode. But copper is discharged because of it is the ion that is lower between copper and hydrogen in the activity series. So copper is discharged. So at the cathode, copper is discharged. So this small copper you bought in the market now gets bigger and bigger because copper is deposited on it. Eventually, if you want to sell, you are not selling what you bought, you are selling a bigger copper. Now, what happens at the anode? Well, even if SO42 minus and OH migrates to the anode, they are not discharged. That's because in the electrolyte, there is Cu2 plus there, and there are some copper here. Just like this copper has been covered or filled with impurity, but there's copper here. The copper inside here sees the copper ion in the electrolyte and says, come, SO42 minus, calm down, and OH, rest, I will ionize. And then it ionizes, like I said, that takes the least energy between the discharge of SO42 minus OH and copper going to ion. Copper going to ion is the process that takes least energy, and that's what eventually happens. So copper electrode, or copper in the electrode goes into ionized and goes into solution, leaving the electron behind. At the end of the day, you see that copper that goes into the solution, the ionized and goes into solution, become discharged here. At the end of the day, all the copper from this impure copper ore become deposited in the pure copper you bought from the market. And eventually, what is left here will become the impurity. After that, the process of electrolysis will stop because impurity is now left. No more copper to be transferred from the anode to the cathode. So that's that about that. So at the end of the day, you have a bigger pure copper rod to sell if you want to sell. Electroplating of one metal by another. You see, electroplating is the process of coating the surface of one metal with another metal, and usually copper, chromium, nickel, or gold, by the process of electrolysis. You see, the process entails one, using the material to be electroplated. For instance, now, we want to electroplate a spoon. So the spoon is the material to be electroplated, and that is used as the cathode. Now, a pure silver metal is what is used as the anode, and the electrolyte is a silver electrolyte. Here we are using silver triazonitrate 5. And so the setup looks like this. This is the material to be electroplated. And so you want the body of this spoon to be covered with silver, and that's called silver plating. And go to the market or anywhere, get a pure silver rod. Use that as the anode. Now, the electrolyte, which is silver 75, ionizes as shown. Obviously, silver is below hydrogen in activity 6, and that's why I said during purification electroplating, the most metals that we use in electroplating are usually metals that are below hydrogen, because obviously when you're using the aqueous substance, you expect them to be deposited at the cathode, and that's what happens here. So silver is deposited at the cathode. So the body of this spoon over time is just covered with silver. Now you have a silver spoon. Well, for a joke though, if you're not born with a silver spoon, you can electroplate yours at home. Now, at the anode, both OH and NO3 migrates to the anode, but obviously none of this will be discharged, and that's because this is a silver rod and a silver ion in this electrolyte. And so rather, this silver ionizes and goes into solution, leaving its electron behind. So eventually, silver is being transferred from the anode to the cathode, and that's what happens during silver plating a spoon. You can electroplate any metal with another metal, but be sure that those metals should be the metals that are below hydrogen in the activity series. Electrolysis of brine. The product obtained during electrolysis of brine are chlorine gas, hydrogen gas, and sodium hydroxide. Actually, brine is simply concentrated sodium chloride and is often obtained from seawater. Now, the electrolytic cell used is known as Solvay-Kernel cell for the electrolysis of brine. So this is the Solvay-Kernel cell. This is how it looks. Now, the anode here is carbon rods deep into the brine, and the cathode is mercury, which flows at the base due to its density. It has a greater density than brine, so it flows in the base. Now, brine ionizes as shown. You see, brine is simply concentrated sodium chloride. So sodium chloride ionizes into sodium ion and chloride ion, while water ionizes into hydrogen ion and hydroxide ion. You see, we have to note the concentration here because brine is concentrated sodium chloride. So high for the sodium ion and chloride ion, and low for the hydrogen and hydroxide ion. And so see what happens here. Let's use this to illustrate that. Now, this is mercury flowing beneath the brine. This is the brine here. We input fresh brine here, and used brine is taken out from here. Now, see what happens in this container. Water is being introduced into this container. Now, see what happens here now. As the mercury flows, it mixes with the brine and collects the sodium ion, because remember, we have sodium and hydrogen going to the mercury. But mercury attracts the sodium because of the affinity mercury has to sodium. It attracts the sodium ion to form what we call sodium amalgam. Now, the sodium amalgams, the moment it flows and gets to this point, it enters into the water and then dissociates. It separates. The sodium stays apart and the mercury stays apart. The sodium will now combine with water to produce sodium hydroxide and liberate hydrogen gas. This is common to group 1 element. So sodium does the same thing as it's expected to do. And the mercury then stays at the bottom again. And that's what you are noticing here. The mercury now come here and stay at the bottom here. And then it's reused again. When the mercury is used again, pick up another sodium again, comes here and forms sodium amalgam, and comes here, enters into the water and separates. The sodium reacts with water again to form sodium hydroxide. Please, this is sodium hydroxide. Sodium hydroxide, and again hydrogen gas. And the mercury dissociate and separate at the bottom again and being recycled again. So the mercury can be reused and reused and reused and reused. Now, so this is an advantage to this, because although mercury is expensive, but can be reused. Now, at the cathode, at the anode, what actually happens? Because mercury is the cathode. At the anode, what happens? Well, chlorine and hydroxide migrates to the graphite rod. But because chlorine has high concentration, and in the activity series, chlorine and hydroxide, chlorine is relatively close to the hydroxide ion. Because of that, chlorine is discharged. So chlorine is discharged, and we can see chlorine gas leaving off from here. So in the electrolysis of brine, we can see that sodium hydroxide is produced, hydrogen gas is produced, and then chlorine gas is also produced. So that's that about that. All you just need to do is to connect this cathode to a cell and the anode to a cell, and that's just all about electrolysis of brine.